as an explicit example where we can locate a Hopf bifurcation and do a little bit of analysis, let's take a look at a phenomenon that shows up in chemistry. This is the notion of a chemical oscillator. Maybe you've seen this experiment in a high school chemistry class. This often goes under the names of Briggs and Roche, Rauscher, something like that. I don't know. But there's this reaction, and you mix stuff together. It was like hydrogen peroxide and some kind of iodate, and you stir it up, and then it starts flashing. It starts changing colors, and it flashes, and it does so at this regular rate. It went from a steady state to something that was oscillatory. That is something that is indicative of a supercritical Hopf bifurcation. Now, let's ignore all the details of the chemical experiment. I don't know much about that at all. And let's move on to a simple model that is meant to approximate what is happening here. And that model is going to be the following. X and Y are going to be chemical concentrations. Let's say your two things you mix together. And A and B are going to be positive parameters. Then consider the following model. dx dt equals 1 minus quantity b plus 1 times x plus a times x squared y. And dy dt equals b times x minus a times x squared times y. What do we do? Well, do the thing. Find the equilibria. Classify them. So I'm going to take the second equation, the one for dy dt, set that equal to 0. Factor out an x. I get x times quantity b minus a times x times y. Is x equals 0 a good choice? No, it's not, because when I substitute that into the first equation, I don't get any solutions, and it's supposed to be a chemical concentration. This is not an equilibrium that I want. So, looking at the second factor, we get that x times y equals b over a. Very good. Now I'm going to take the first equation for dx dt, set that equal to 0, and I'm going to isolate a factor of x times y. Substituting in b over a for x times y, I get that 0 equals 1 minus quantity b plus 1 times x plus b times x. That is 1 minus x. And that's it. Our equilibrium happens where x equals 1, and using the previous equation, y equals b over a. Very good. And so with everything in place with our model, with our single equilibrium at x equals 1, y equals b over a, I take the right-hand side of that model. I'm going to call that capital F. I take the derivative of that. What is that equal to? I've got to compute a couple of partial derivatives here. What do I get? The partial of the first term with respect to x is minus b minus 1 plus 2axy. The partial of the second equation with respect to x is b minus 2axy. The second column of the derivative is comprised of the partials with respect to y, that is ax squared and minus ax squared respectively. When I substitute in x equals 1, y equals b over a, I get the matrix b minus 1 minus b, a minus a. What's the determinant of this? That's, let's see, negative ab plus ab. That is just a, and a is positive. So I have positive determinant. The trace is b minus 1 minus a. With everything that we have assembled, we can conclude that a Hopf bifurcation occurs whenever b equals a plus 1. Now, this is a little different than a lot of systems that we've looked at because there are two parameters, and there's a two-dimensional parameter space. And within that two-dimensional parameter space, what we have is a line of Hopf bifurcations. So as you cross this line, moving from one side to the other side, you've got a Hopf bifurcation. You've got a limit cycle being born. But, of course, the question is, where is the limit cycle? Is this a supercritical or a subcritical Hopf bifurcation? With additional work, one can show that the periodic orbit, the stable limit cycle, lies above this line in the parameter plane. We have a supercritical Hopf bifurcation happening here, but that is by no means obvious. With respect to this and other examples, there's so much more out there that one could do. There are so many examples of Hopf bifurcations. Have you ever been driving in a car and then all of a sudden it hits a certain speed and starts resonating? That's a Hopf bifurcation. Do you see blinds where the wind blows at just the right speed and then they start to flutter? That's a Hopf bifurcation. So many examples, we could fill a book with them. But what I want to get to is the question. The question, the thing that is genuinely difficult to figure out when you encounter a Hopf bifurcation is it supercritical or subcritical? Where is the limit cycle?